Hello everyone, my name is Anthony Nunez, and this is part 2 of our tutorial series on how to use National Instruments AWR Microwave Office. Again, this video series is intended for the students of RF Circuit Design at Florida International University. We will be continuing directly from where we left off in part 1, where we designed this two-way Wilkinson power divider using the circuit available in the textbook in figure 7.8b. If you have not done part A or part 1, please go back. The video can be found in the video description. Click on the link, go do part 1, and then come here to continue on. So there's one thing that we need to address. There's a little mistake that I made in part 1 in terms of one of the component values. This resistor over here on the right, I set to 2 times Z0 according to the figure in the book, assuming that our Z0 is 50 ohms. However, we have to remember that the variable we declared over here, Z0, is actually the width of the transmission line to get 50 ohms worth of impedance using our FR4 substrate. So technically, instead of getting a 100 ohm resistor, we're actually just getting 2 times 2.9. So we're going to come over here to the actual resistor value, or double click on it, just type in 100 and hit enter. So what was happening last time is that when we were looking at transmission, the isolation of our port 2 and 3 was not as low as we would like it. And that was caused by that resistor, as we know from theory, helps with the isolations between ports 2 and 3. So we rerun the simulation, and we see that now our isolation is greater than 10 dB. And so in this video, we're actually going to be talking about the concept of optimization. Now, optimization, as the name implies, allows us to optimize our design. These design tools have optimizers built in, which allow us to find the perfect values for different parameters and variables in our design in order to achieve certain goals. We, as designers, pick the goals that we want, and then we let the optimizer loose on those goals in order to modify our design and find the optimum values to achieve those goals, if it is possible, with the constraints that we will be setting on the variables. Now let's look at our design really quick. So we have several things that we can actually affect here. We have arbitrarily chosen that our feed line and exit lines are going to be half wavelength. As we know from theory, they don't exactly have to be wavelength. What they cannot be is quarter wavelength. So technically we can do anything between quarter wavelength and half wavelength, or anything under quarter wavelength. And so we're actually going to be optimizing these lengths to see if we can shorten these a little bit in order to miniaturize our design a little bit. So another area that we might be able to affect is the actual quarter wavelength segment that helps with doing the power division. As we know, we arbitrarily chose that this was going to be half and half, so half a quarter here, and then the bend. However, this bend introduces a certain amount of length to the transmission line, so that we can go and optimize the quarter wavelength variable to adjust for the fact that this corner adds wavelength. So we can get closer to an actual quarter wavelength overall length on these two segments. We'll be able to use the optimizer to do that as well. So we're going to do one step at a time to show the different features of the optimizer. And the first thing that we're going to have to do is come over to our project pane as we showed last time. And we'll see a field called Optimizer Goals. We're going to right click and click on Add Optimizer Goal. This is going to bring up the new optimization goal window. And we're going to see all of our measurements that we are currently graphing are also listed here. If you would like to optimize a measurement that is not listed because you're not graphing it, you can hit the New or Edit Measurement window. So then we have several other features here. First, we have a goal type. We can see if our measurement is greater than the goal, lesser than the goal, or equal to the goal. We can also specify the frequency range for which this goal must be met. The goal weight, the higher it is, the more priority this goal will be given. Sorry, wrong field. The weight is here on the right. So the higher the weight is, the more priority this field will be given. The goal, unitless, has to do with what we are trying to accomplish. So let's say we were trying to improve the match. The match has to do with our S11, or our impedance bandwidth. And normally, as we know from theory, we want less than -10 dB on our S11 in order to get a fairly decent match for whatever characteristic impedance it is that we're using. So First thing that we're going to do is we're going to try and improve the isolation between ports 2 and 3. That's going to be our first goal. And currently we've accomplished more than about an average of actual 15 dB of isolation. So we're going to go lesser than, and we're going to say let's try to go for 20 across the entire board. We're going to leave the range of frequencies from the minimum to the maximum. So this is basically going to try to match this goal for the entire frequency span from 4 to 5 gigahertz. And we're going to go ahead and leave the weight as it is, hitting OK. If we go back to our transmission graph, we can see that, it's not showing. We'll hit optimize. Oh, it was supposed to be less than -20. So in the graph, you'll see this new line with these dashes along the line. The dashes show the basically upper boundary of that goal. So basically we're saying that from -20 down is our goal. If they were flipped the other way, we're basically saying from -20 up. If it just shows kind of like a thick line with dashes on both sides, we're basically just trying to match the value itself exactly. So we can see that we're less than -20 dB. So this is basically 20 dB of isolation, between 4 and about 4.1.5. We want to get this whole curve below -20. So exactly what variables are we going to try and optimize? Well, we know the isolation directly has to do with this resistor. So we're going to try to do a single variable optimization of a parameter for a given component. You can do that by double-clicking on the component to bring up the properties window. And then here we can see the value of the unit, and we can also see these different check marks. We're going to hit optimize and constrain. And then we're going to set the lower boundary to about 80 ohms and the upper boundary to about 120 ohms, and then hit OK. So now this means that we're only going to be optimizing this variable for this specific goal that we have set. The way we do this is we go simulate, optimize. This will bring up the optimizer tab. We have different optimization algorithms. You can find out what these do inside of the documentation, which you can read by hitting the help button down here. We're going to select gradient optimization. This is the best type of optimization when we have a few variables. When we have many different variables, the different optimization method you're going to want to use is actually random local. If you want to find out more about how these optimization methods work, again, refer to the documentation. We're going to leave our default parameters of optimization as they are, and we're going to go ahead and hit start. So the optimizer should be running, and we can see that the curve is not really moving anywhere. So if we go here and we click on vars, it will bring up the variables pane. Another way to bring this up is by hitting this button up here in the actual toolbar where it says variable browser. But we're just going to go ahead and click down here, vars. We see our one design. We can see the resistor value was lowered to 95.43, but it basically did not move the line. So what does this tell us? Well, the isolation cannot be improved any further through the resistor itself, which means we're going to have to try to improve the isolation in some other way. So I'm going to go ahead and uncheck optimize, so we will not try to optimize this variable anymore. I'm going to go ahead and set this back to 100. You can also go back to your design, again through the tab navigator up here, and we can just make sure that we're at 100 ohms. Okay, so what else could we affect? Well, we said that we would like to maybe fiddle with these half wavelength feeds and exits. And so we're going to go ahead and we're actually going to create some new goals. We're going to leave this isolation goal as it is, and we're going to add some new goals. We're going to add an S31 and an S21 goal so that we can try to get to 3 dB of split, because we're currently doing about 3.5. So we're going to try to go for that. So we're going to do 3.1 equal for the entire frequency span -3, and hit OK. Add another goal equal to -3, 2.1, OK. Go back to transmission. Now we see these lines here. These lines are the exact goals that we're trying to meet. We're going to hit go. And you'll see that We have a line with dashes on either side. That means that the goal is equal to. Again, these dash lines over here means that the goal is less than. Now we're going to look at our design and see what we can fiddle with. Sorry, go back to the navigator here. So again, it's just a half wavelength variable. So the way we have two ways of making this an optimization variable. We go here to the variables that we've created. You find the one, put the mouse over it, right click, properties, and it will bring up the properties for that variable. Then you can check optimize constraint and put the constraints. The way I prefer to do it is by actually going to the variables browser, finding the variable of interest by name. So here we have half. It's 18.59 right now. We're going to go ahead and hit optimize constraint. Now, do yourself a favor, and before you change these, make sure that you write the default value. In our case, default value is 18.59 for the half variable, as you might lose this and you don't want to lose it. Okay. For constraints, it's about 18.59 millimeters. So let's be arbitrary and let's choose between 15 and 19 for that. And that's the only variable that we're going to be touching for now. Then we're going to go ahead and hit start and look at transmission. Just give it a second. We see that the curves are not moving whatsoever. Alright, so these parameters didn't change any. Let's look at the match. Well, our S22 and our S33 are very well matched. Or basically, we're going to say less than negative 30 dB. And that S11 is also very well matched, less than our negative 10 dB here. So this is pretty good, but the transmission didn't move any. So let's see what happened to the variable. Well, the variable moved up to the upper limit. Okay. Let's see what happens if I set this to 15. What happens then? I'm not going to run the optimizer this time. I'm simply just going to click on this. Well, we see that our isolation tipped up a little bit. Our match remains just as good. But when we look at the layout, it's a lot more compact. So this type of manual modification of your variables actually gives you a pretty good idea. You can use the built-in optimizer, or you can tune things by hand, and it gives you a pretty good idea. As we know, as long as we're not doing a quarter wavelength, we can do less than a quarter wavelength, or between a quarter wavelength and a half wavelength, and technically it should not affect our performance at all. So in this case, we're just going to leave it as half. Okay, so what's left here that we might be able to play with in order to get better performance? Well, as we know, we established in the beginning that this leg is supposed to be a quarter wavelength. However, we did a 50 split and a 50 split, but this corner here adds a little bit of length. The signal still, the wave needs to go along this half and then go through here and then go through here. So these two legs are a quarter wavelength, but it's just over a quarter wavelength. So we're going to try to tune these down in order to get the actual value that we will need. So we're going to uncheck optimize on half. We're going to check optimize on quarter. We're going to constrain, and we're going to go from about 8.5 millimeters to about, let's say, 9.50 and see what happens. Then we're going to go to goals, start, and transmission. Okay, so now we see that the isolation got pulled down a little bit better. If you go over the curve and click on it, you'll get a little tooltip that shows your values along that curve. We can see that our actual splitting remains around the negative 3.5 dB mark. So that has not improved, but the isolation between ports 2 and 3 has improved. What happened to the variable? Well, the variable actually dropped considerably down to the 8.5 mark. So what we're going to do is, because we see this red, basically meaning that we're on that limit, we're actually going to go ahead and actually lower that a little bit more. So we're actually going to say 7.75. Let's see what happens with that. We're going to go to goals and hit start. Okay, now click on the line, still 3.5, but our isolation is way better. We see less than negative 20 all the way up to about 4.7 gigahertz. So again, as a designer, you have to decide what are you willing to sacrifice. in order to improve your performance. Are you willing to take the negative 3.5 split in order to improve isolation? So you get better isolation between ports 2 and 3. Let's see what the match happened here. Okay, we're improving the S11 match. And I think we're sacrificing a little bit of the S22 and S33, but that's okay because we're improving the S11. So that is okay. Let's keep playing with this a little bit. What else could we possibly do? Well, the quarter wavelength is getting even smaller. Let's look at our layout. Control A, snap. Okay. So I think we can keep miniaturizing this a little bit. So as long as we do not mess with these values, I think we should be okay. So what else can we do? Okay. So let's focus here for a second, actually. Between the quarter wavelength leg and the actual exit length, there's a pretty big jump in width. This is going to attribute, or is going to contribute to our mismatch as far as S11, S22, S33 are concerned. So what could we do here in order to help improve the match potentially? Again, so we're basically going to establish a hypothesis, design an experiment, and go ahead and test our idea and see if it actually works. So I'm going to argue that we should probably put some kind of impedance matching circuit here in this threshold to see what happens. We're going to go to elements, we're going to go to actual microstrip, we're going to go to other, lines. Okay, so under lines, we're going to grab M taper $. This is an intelligent tapered microstrip line. Basically what this is going to do is, instead of us having to define the input width and output width, it's going to intelligently detect the adjacent lines, get the width parameter from them, and then inherit them directly. So it's going to make our life a little bit easier when it comes to designing. We're going to go ahead. We're going to grab this here. We're going to move it over. We're going to delete that. Let's make some space. And let's drop the taper in here. Let's see if it was a, wow, perfect measurement. I'm going to copy it down. Perfect. So, let's see here. We're going to add actually a new variable. Call it taper length. We're going to set it to 1 millimeter. And then we're going to go ahead and shift click on both of the tapers, right click on one, hit properties. This is going to allow us to simultaneously edit both tapers. And we're going to go ahead to the length parameter and we're going to set this to taper length. And close. Oh, I didn't hit accept. So properties, taper length, okay. Now it actually propagated through. We're going to go to the variables parameter. We are going to find taper length. We're going to hit optimize and constrain. Let's stop optimizing the quarter wavelength. We're actually going to play with this length. Let's go between let's actually go between 500 microns, so 0.5 millimeter, and 2 millimeter on the taper length. And what we're also going to do is, because we don't want this to actually add any additional length, we have the option of subtracting. So let me show you how to do this. We're going to select both of these exit lines. We're going to hit properties. And then we're actually going to do a little bit of math. So we're going to go to the length, and we're going to have half minus taper length. And this is going to remove the length of taper from the actual half variable that we're using. So that's going to overall shorten the lines, so that basically our half variable is going to be starting from the beginning of the taper all the way through the end of that line. Let's actually see a preliminary result of what happens here before we start optimizing. Okay, so this doesn't really help any. Let's look at our match. Again, we actually affected the S11 a little bit. However, the S22 and S33 seem slightly unaffected. I think this was lower before. But again, we're going to optimize. So we're going to go to goals and we're going to hit start. And it already stopped. So we check. Nothing happened here. See a pretty linear response here, so that's not helping any. Let's go to variables. Well, the taper is basically getting shortened, so a hypothesis I have here is that potentially adding the taper is not really helping any. So let's actually lower this constraint even more and see what happens. If it goes to the bottom limit, it's the optimizer basically at that point is telling us that this component is as it approaches 0 in length, it's like basically remove it, it's unneeded. We're going to go to goals, hit start, it stopped, variables, yes, exactly. So it's basically saying that that taper is not really helping any. So we're just going to remove it here, and we're going to grab these two things, move them back. So at this point, basically, we can't really make much of a decision on what we're going to be doing here. So let's actually try something. Let's make the radius of the bend variable alongside the quarter wavelength, so that both of these variables are moving around the same time. So first of all, let's go to the design. Let's remove this variable because we're no longer using the tapers. And then we're going to adjust the half wavelength. Again, let's do both at the same time. Shift select both properties in the window. We're going to convert this back to just half. Hit OK. We're going to go to variables again. Optimize quarter. Optimize radius. Constrain the radius. Let's go from 1 to 3 millimeters. And let's lower this lower boundary here to 6 millimeters on the quarter. And we're going to hit go. And I already stopped. Look at the layout first, see what happened here. Okay. Okay. Our isolation is all under -20 now. We're still at about 3.5. What happened to our match? Okay. So now our match is completely under -20 dB for the S11, and we're looking at pretty much under -35 dB on S22 and S33. So at this point, I'm just going to bring this video to an end. I think we've done plenty as far as optimization is concerned. In the next video, we're going to be doing the actual electromagnetic simulation of the circuit. This is going to give us a much more accurate representation of the real result we would get if we fabricate the circuit as is and test it. And then also another thing that we're going to be doing in the next video is the method of extractions, which is going to help us do the EM simulation. And we're going to tie together what we learned in this video about optimization, and we're going to combine it with method of extractions. This is going to allow us to do optimizations on the actual EM simulation results, allowing us to optimize our quote-unquote real results instead of just these theoretical circuit results. Anyways, thank you for watching. Leave any questions you have in the description. Find the link to part 1. Leave your questions in the comments and find a link to part 1 in the description. We'll see you next time for part 3, and have a nice day.